should be here. He's going to Kentucky next year. Find out where he is. So as part of his PhD, so he will help Steve and take some lectures there. He likes advanced. What is correct? He had to go or something? Okay, he has a presentation. All right, Steve, welcome to the stage, and thank you so much for coming again.
Okay. Again, it's great to be here. This is my 4th time. I missed last year because I was asked to be chair of the department. And somehow the dean didn't feel that taking a couple of weeks off in the middle of the semester was acceptable. So I'm going to talk about lifetimes all the way from, well, let me say a couple of other things before I begin. John was kind enough to say how he credited his education to public support. My education was also publicly supported. Without public support, I wouldn't have been able to go to university. So it's important. I talked here 2 years ago about the same topic, and I made a mistake. I started at the wrong level. So this time I'm going to start at a low level. If you don't follow me, interrupt me, because I may turn around and ask you a question. And it's important that we be on the same page. The other reason I like to be here is I'm treated so well. You may recognize this poster. 2 years ago when I was here, I looked over and Nico was crawling on the floor taking a photograph. So this is how that poster came. It's really one of my wife's favorite photos. She says, I look so intelligent. And you can see I'm looking up, and she says, I know something. She doesn't say that about most of my photographs. Okay, I want to talk about level lifetimes, all the way from 10 to the 32nd years to 10 to the minus 18 seconds. That's roughly 47 orders of magnitude, and I've got, I don't know, half an hour or so to do it. But first I want to say where I'm from. This is the United States, of course. This is the bluegrass state of Kentucky. And to locate it with respect to some other famous places, these are the national laboratories in the United States: Brookhaven, Oak Ridge, National Superconducting Cyclotron Lab, Argonne National Lab, Los Alamos, Berkeley, and Livermore. And I put Triumph in there also. It's almost an American laboratory. It's roughly 50 kilometers inside Canada. I've worked at all of those, I think, except for the NSCL. Kentucky is famous for a number of things. Fried chicken is probably the greatest claim that Kentucky has in the world. We like to think of ourselves as the horse capital of the world. We raise thoroughbred horses. It contributes a lot to the economy and also to society. These are scenes from campus. This is our new library. Well, it's not so new anymore. There are seats for 5,000 people in that library. And it's interesting because it was built at just the wrong time. 10 or 12 years ago, what happened to our libraries? They moved to the desktops of our computers. So it's a nice study hall now, and students enjoy it thoroughly. This is a view outside the chemistry physics building. This is the Accelerator Tower. We have a small Van de Graaff, and I'm going to say a few words about that. How'd that get in there? This obviously is Professor Wood. For many years he's been looking for vibrations, and you can see where he is. You probably recognize this in the background. John wears strange hats. Okay, the Accelerator Laboratory in UK. I mean the University of Kentucky. This is what it looks like on the outside you saw. This is what it looks like on the inside. You can see it's very good because on the outside and the inside it tilts to the same direction. It's a single-ended Van de Graaff accelerator. I don't want to say very much about the targets and the various things we do, but one of the things that we specialize in is in femtosecond lifetime measurements. And I'm not going to talk about those necessarily this afternoon. I'll talk about them tomorrow. There are a number of things that I would point out about our facility. It is a hands-on student-run facility. Without students and postdocs, the facility doesn't run. Some miscellaneous facts. The one that I'm perhaps proudest of is the research program has continuously been supported by the National Science Foundation for over 50 years. I haven't been at the University of Kentucky for 50 years, although it may look it, I may look it. But it really is a testament to the kind of science that was done for over many years. Our average publication's about 10 per year. There are some other facts that are shown here, but it's a small facility, but I think a very active one. Again, the photograph, this is the inside of the accelerator. This is the ion source. These are just some comments about the various properties. We have light ion beams, protons, deuterons, helium-3, alpha particles, and we can run neon beams, but not with enough energy to really do any nuclear physics, do atomic physics with it. The voltages it runs are from half an MeV up to 7. One of the things we have very nice with this facility is we have very nice pulsed bunched beams. So we have very good time structure on those beams. This again shows the inside of the accelerator. You can see the tank just disappearing at the top of the screen. There's somebody who's to give some perspective of size. This is the ion source assembly. And again, the pulsing and bunching rates are less than 1 nanosecond. And this photograph really doesn't have anything to say about it, except you can see the nice color of the hydrogen plasma source. Okay, we specialize in, well, I shouldn't say specialize, we use the inelastic neutron scattering reaction. Do you have your pointer?
Ah, yes. Very happy to use it. Sorry, I was...
Well, just as you were honored for John to use it, I'm honored to use yours. And I don't want John to one-up me.
Because of the principle that they balance, it's reversed for me. Okay.
Okay. So inelastic neutron scattering is a very simple reaction. And if this is a fast neutron coming into a target nucleus and it scatters into some direction, then the nucleus is going to be excited, it's going to recoil, and it's going to de-excite by the emission typically of gamma rays, and we detect those gamma rays to yield us a cooled nucleus. Now, what kind of reaction is that? No one knows? What? No. Well, is it a compound nucleus reaction? Could be. You probably don't have enough information yet to say whether it is or not. If this is the same neutron that came in and emerged, we don't know. If that's a different neutron, it's obviously going to be compound nucleus reaction. And at the energies that we typically use, they are predominantly compound nucleus reactions. So this means that you get all of the properties of a compound